Hello and welcome back to the Oxford Online Maths Club for another episode. Today I'm joined by Leo. Hi Leo, say hi to the stream.
Hi guys, my name's Leo. I'm from Belgium. I'm in my first year DPhil, but I've been in Oxford for 5 years. And the
Brilliant.
fun fact about me is that I once tried to make my grandma's soda bread, but I forgot to put baking powder, and so it turned into a brick. And because I don't like food waste, I ate that brick for the following week.
learning about cooking is hard, right? It's almost as hard as learning about maths. Um, I don't know if I don't know what the
It was hard
soda in
at
soda
first.
bread is. I don't know if a bread without soda bread without baking powder sounds like maybe soda bread without soda. Maybe we've learned that doesn't leave you with bread.
Yeah, yeah, I guess I forgot my brain somewhere else that day.
Oh no. What's your default on? Don't say bread.
No. So my DPhil is in population genetics. So if you imagine just like animals or particles moving around in space, like for example, rabbits and foxes moving around in space, and you want to model that mathematically, and you want to get some results, like is there an equilibrium of foxes and rabbits, for example,
Nice.
with but probabilistic, so it's random.
Okay. I think I've heard of population dynamics before. I'm trying to remember if we've talked about it on the Maths Club before. Maybe a topic for another day.
Mhm.
Is details of how that kind of probabilistic modelling works. Because my plan for today, in the thumbnail on the video, is to talk about Fermat numbers and Fermat primes. Someone in chat has spotted already. Yes, it's another thing by Fermat. Um, at the start of the show, though, we always check how everyone's day is going. So I'm going to run the poll. I'm going to run the poll in live chat. If you're watching live and you would like to join in the live chat, it's at slido.com/OOMC, which stands for Oxford Online Maths Club. I can't remember the name of my own show, and that's a solid 1-star vote straight away. Leo, how's your day going?
Oh, it's going pretty well.
Somebody in the chat's asked, what's it actually like doing a PhD?
Um, it's very, very different from doing a bachelor's, even a master's, because it's very unstructured, but you get to explore your own things in a way. But you don't have the same regularity as you have for school or for a bachelor's, which I think, in my opinion, are pretty similar.
Okay, so now
And then
from
you get
that's
stuck in
interesting.
yeah, and I'm realizing that you have to be very pragmatic because there's too much knowledge out there. So if you're someone who wants to know everything, that's just not possible. And so you have to get stuck in very specific topics.
I've seen some debate about who was the last person to, in some sense, know everything, and
I've heard von Neumann, but
yeah,
I don't know how true that is.
knew a lot of
Well,
stuff. At least a lot of mathematics, right? If that's your goal, to
mhm.
say something interesting about all mathematics, um, it's absolutely impossible these days. There's kind of curse of knowledge. There's way too much stuff out there. Um,
Mhm.
Cool. People are voting on how their day was in chat using a star system. Seems like a bit of a 4-star day. We're always watching out for people who vote 1 star or 2 stars. I think the 1 star vote has retracted their vote. I didn't even know you could do that. So maybe that means their day has
That's a
already
good thing.
improved.
Yeah.
If not, then let's hope that large primes is the thing that they need in their day, because that's where we're going. Um, okay,
Mhm.
okay. Um, Fermat numbers work like this. They're called usually capital F subscript n because it's a sequence of numbers, and it is 2 to the power of, deep breath, 2 to the power of n, and then plus 1. So,
Mhm.
huge number of 2's multiplied together, plus 1. The first few terms are 3, 5, 17, 2, 5, 7, 65,537, and then some more numbers. We were talking before the stream started about just how unimaginably large these numbers are. Leo, do you want to have a go at trying to explain just how large 2 to the 2 to the n really is?
It's incomprehensible. I mean, I, I don't know if I can make sense of it myself, to be honest.
So I
But
suppose.
it's like if you take a number and then you square it, except you square it n times
Oh right, yeah, that's a good point.
because of the recursive relation, if you know.
Right, so it's something to do with squaring each time. That's a good point. What's
Yeah,
this? So this recursive relation you've mentioned is a relationship
yeah,
between Fermat numbers, which is
yeah,
something like I can't quite remember. It's something to do with the square of the previous one, right? How
yeah.
does it work?
So it's the previous one minus one squared
Uh huh.
plus one.
Oh, I see. Okay, okay.
You
Um,
can just imagine squaring every single time.
I see. You've taken off the one. You've got all these big stack of powers of two, and then you've squared it. And then, if I really think about squaring, that puts another two upstairs, and the powers multiply or something.
Because exponentiation, when you think about it, is already huge, and that's multiplying by a constant every time. So this is squaring every time.
Yeah. So something I've been thinking about is sometimes you see exponentials like this, um, and to try and understand exponentials, people sometimes put them on like a log graph. So instead of y and x, people sometimes plot log y. And that's a good idea if you have exponential data because then you get a kind of linear function instead. It looks linear. This is good if you want to understand exponentials. The Fermat numbers grow so large that if you put them on a log chart or logarithmic scale, then you get an exponential. So you need to do it again. Well, that's really really large. Hi to people in chat, by the way. We've seen Raphael Darley. Somebody in chat also did mention they had a computer science and philosophy offer. Raphael, I think, is currently a CSMP student. Is that right, Raphael? Just talking to chat. Sorry, Leo. Miles asks, what's so interesting about the +1? And I guess it's that we're looking for primes. If you don't have the +1, then you don't get very many primes out of this sequence. If you do have the +1, then question mark, question mark, question mark. Let's go there. Because the thing these things have got in common are all prime. So this is a strong start for a sequence. Something that might happen with the rest of the sequence. I try not to give the game away yet, but during the sequence, some things might happen, right? It would obviously be very exciting if the rest of the sequence, was maybe all primes. That would be extremely exciting. It would also be exciting, I think, if there were none of them were primes, in a way, or like infinitely many of each. I don't know. That one seems the most likely somehow. They're kind of some primes and some non-primes. And I'm putting a big question mark here. What do people in chat think?
There could be finitely more of them.
Yeah, that's a good point, isn't it? I haven't quite done. That's not an exclusive set of options. Okay, help me to think this through. Sorry, Leo. Because they're not mutually exclusive. They could
No,
be.
but if
Yeah, I'm missing like an option for finitely many.
yeah,
Primes, and I guess by symmetry I'm also missing an option for finitely many. Oh, pen's gone a bit. Finitely many not primes. I think those are now all the options. Sorry, got distracted. Someone in chat said they have an offer for maths and no longer know why they ever thought about applying for physics, which is great news. They've got an offer for maths. Congratulations if you've got an offer, by the way. It's the week when Oxford offers have just gone out. I don't know if you can remember that far back, Leo, to when you just found out you got an offer.
yeah, I think I do remember that far back.
Okay.
I actually got my offer in maths class.
You were in the classroom.
Yeah, I was in the classroom
What does
and
that
checking my email,
mean?
which I wasn't supposed to, but
That's a pretty good way to find out, I guess.
yeah,
Surrounded by more maths, knowing that you'd be surrounded by more maths for maybe 3 or 4 more years after that.
yeah.
Um, I found out in an actual physical letter, which is I do not recommend. Um, good times. I'm too old. Person in chat got their offer in for maths and philosophy in a philosophy lecture.
Oh, that's quite funny.
Symmetry, beautiful.
Yeah.
Checking email in a class has really resonated with our audience. Good job.
Yeah.
Right, okay. Here is the answer to this question, by the way, which I think is nuts. We know they're not all primes. In fact, Euler proved that the next one in the sequence is not prime. But we don't know which of the rest of the other ones it is. We just don't know. It could be any of these. And I think this is a really interesting problem because it's really easy to state. It's just like a load of 2's multiplied together plus 1. Is that prime or not? And we just completely don't know.
Yeah, our tools are not strong enough.
In some sense, this sort of thing is true of a lot of problems in prime number theory, that it's just really hard to prove that in general things are prime or not prime. Well, that's not quite true, is it? You can prove things are not prime quite easily. For example, if instead of 2 to the 2 to the n plus 1, if there wasn't a plus 1 there, then you can prove that infinitely many of those terms are not prime. So I've overstated it a bit. Question from Shrist in chat. Are only integers part of the sequence? Can you look at negative integers? Good question. People don't normally look at negative integers. People normally start from 0. But there's nothing to stop you looking at negative integers if you want to. I guess all of those numbers are like 1 and a bit. So they're not going to be primes because they're somewhere between 1 and 2. But I can't see anything wrong with looking at those numbers to see what happens.
Wait, negative integers. What would be negative?
They want to put n as a negative number. So they want to just try it just to see what happens. I think does the recursion relation still work? I'm not sure. It's possible this squarey thing still works.
Because
maybe not.
If n is negative, to the negative number, don't you get radicals? Don't you get like the square root of 2?
Oh no, what am I thinking? But it's 2 to an integer. It's not 2 to a half. So I think these are rational at least.
Oh yeah. They should be.
I think this qualifies as good question, room for investigation.
Yeah.
Yeah, I think the recursive definition maybe even still works, but now I'm nervous about square roots as well, actually. If you try and do it backwards, you're like solving a quadratic to find the previous number. Wait, quadratics have got 2 roots. What's going on? Anyway, down a rabbit hole. Back up. Because I was trying to set you up, Leo. Just before we went live, Leo told me that a huge class of numbers that look a bit like this are not prime, and Leo can prove it. So I'm going to try and get Leo to do that. Sorry, but by the way, chat's agreeing with you. I'm just wrong. That these are not rational. The previous one was root 2. Sorry, carry on.
Yeah, with -1 you get root 2, I think.
Yeah,
plus 1.
Correction accepted. Thanks, chat. Thanks, Leo. Right.
So the question that motivated this is, why do we only consider 2 to the 2 to the n plus 1? So what if you considered 2 to the m plus 1 for any other m? And so if a number m is not of the form 2 to the n, then it must have a divisor which is odd, right?
Yeah, okay. So there's not just a big pile of 2s, then its prime
It's not
factorization
just
has
a
got
pile of
something
2s.
else in it. Okay. It's got an odd
Yeah.
factor, I'm going to say. Okay.
Yeah. And then you can write m as some, and then here's the trick. If you just have m as something odd times something else, then it's as if you were considering 2 to the something to the power of an odd number. Oh yeah, m equals pn.
Yeah, I'm not really sure what I want to call the other parts, but sure, I want p as an odd prime for that odd prime factor, right?
Yeah, p is an odd prime.
Wasn't quite sure what to call the rest of the other bit. Okay. So then m's got an
I
odd
mean,
factor.
for this, p could, yeah, and then you get 2 to the n to the p plus 1. And it turns out that there's an explicit factorization for that, which you can write down, which is quite nice.
It uses the fact that 1 is equal to 1 to the power of p, right? And that this is, I guess, and there's a factorization for the sum of 2 odd powers.
Yeah, there is.
People in chat, we saw the sum of 2 cubes last week. We talked about 10 cubes plus 9 cubed and using that to factorize things. That generalizes nicely to odd numbers.
Yeah, if you try for power of 5, for example, you get a very, very similar expression. If you try for 7, you get something similar as well.
Sure. The factor is always x plus 1, right? I think.
Yes, it is. Yeah. The
So-
reason is, as you said, -1 divides.
Yeah.
-1 divides.
I remember.
As an
that.
x equals -1 is a solution.
We came up with a polynomial way, right? Like, so -1 is a root of this polynomial. So factor
Yes.
theorem, x plus 1 is a factor of this polynomial. Or in general, maybe I should have written p. Never mind. I'm going to go 4 in here. I think this is right. I'm going to try and factorize
Yes,
it out
yeah,
just as
this
a
is
concrete
right.
example. Do you want to talk about what patterns we get as we do it?
Yeah, you get the alternating minus x cubed.
Okay,
And it's similar. It's similar in a way to the formula you've seen for sums, which is if you have 1 minus x to the 5 divided by 1 minus x, you get the sum, right?
Yeah.
Except here you can plug in minus x, and then you get the sum x to the 4 plus x cubed plus x squared plus x plus 1.
That's brilliant. Cool. So this is you're using the geometric series fact from A level.
Yeah.
Have people in chat
Yeah,
seen
exactly.
the geometric series fact? I'm no longer sure. I'm going to put bracket, exclamation mark and brackets because I think that's clever. What a great way to factorize it. Okay, there you go. What a good detour. A detour into the factor theorem and geometric series. Maths never stops amazing me with the way that things just get connected together. You'd be doing prime numbers and polynomials and just, where's the boundary, right?
Yeah, it is quite amazing. I've used the factor theorem recently, actually. It's something I was learning about, so.
Ooh, okay. Cool. So wrapping up this proof then, I'm just going to write a small note over here. Similarly, for p, any odd number. I think they get the idea in chat.
Yeah.
Except more terms. And my pen's gone really slow, so I'm going to put a little square there for a proof. I really like this. So if you're doing 2 to the big power and adding 1, and you want to get a prime number, then you've got to look at the powers of 2. One request in chat for us to just do the geometric factorization trick again, and that is that I think let me say it slightly differently. So maybe you agree in chat that this factorization works. If you multiply out both sides, then it works, but it looks kind of mysterious. I think one way to say it is that Leo recognizes this term in brackets as a geometric series. I don't know if that's fair or not. Yeah. It's a geometric series, kind of written right to left with common factor, common ratio minus x.
Hmm. Yeah, I think one way to think about it is use the geometric series for 1 minus x to the 5 divided by 1 minus x. If you have x to the positive power when you replace by minus x, you still you still stay with a minus sign because minus 1 to a positive power is 1. Whereas when you have a negative power, it changes sign, which is exactly why this factorization works, but only for odd numbers.
Right.
So if you
Okay.
tried again for even numbers, you would see this factorization doesn't work.
Okay. Okay. So this is. Let me try and write this down correctly. There's a challenge.
Mhm.
N plus one here. Oh, I guess
Yeah.
N of I've misleadingly used capital N. I shouldn't have done that. I'm going to put a different number. N tilde, the Spanish N.
Mhm.
Plus one, one minus. Not Spanish N, but you know what I mean. Okay. If you're Spanish and in chat, let me know what the name of the letter is for N with a tilde thing on top. Or if you're not Spanish but have access to Google search, then. Anyway, I did a lot of my PhD. If you run out of letters, just decorate the existing letters. Did that
Mhm.
quite a lot. Big fan of putting hats on things, the little carrots on
Yeah.
different variables.
Yeah. That's so useful. And you can also use all the Greek letters you want. Mathematicians love to use the Greek letters.
I made a table at one point to check if I'd used all of the Greek letters or not, and I'd used all of them except for the ones that look like Roman characters.
Hmm.
There's some in the middle that are just like I and O that you shouldn't really expect people to distinguish between I and
No, definitely not.
iota. Right, okay. So I like this proof. Thanks for doing this, Leo, because this means that our search for primes of the form 2 to the m plus 1 is just primes of the form 2 to the power of 2 plus 1. The only things
Hmm.
that we've got left over is I just iota with a dot on top. When you put it like that. Quick shout out to Turkey, who have another letter that's a bit like I, but has a different symbol on top. Right, good, okay. Not a language class. Well, it's supposed to be a maths class. Here's what we know about Fermat numbers. And when I say we, I'm using this kind of mathematical community.
Then
Yeah, general we, yeah. Not just me and Leo. The first 5 numbers in the sequence are prime. We know they're not all prime. Euler proved that the next one's composite. And all of the ones we've checked after this one are also composite. The suspicion is maybe, and it is a maybe, but maybe all the rest are not prime.
hmm
But that is just a hypothesis, it's a conjecture, it's a guess. I've seen some really quite dodgy maths to try to justify that, which I'm going to do, and then you in chat and Leo can call me out on it and say why it's not good maths. But I'm going to do it anyway. There's this kind of heuristic for why you might expect the rest to be not prime numbers. Here we go. So I feel quite bad. Leo's presented some amazing maths. Now I'm going to present some really dodgy maths. So there's this thing called the prime number theorem. The prime number theorem is an approximation to the number of primes below a particular point. It's a sort of asymptotic result. It's good for large numbers. So if you're looking for the primes below some number n, it says that this is about n divided by the natural log of n, which is pretty good. Yeah, a cool in chat says it seems arbitrary that it just stops after 5 prime numbers. I'd go further, I'd say disappointing that it's 5 in a row and then maybe no more afterwards. Prime, maybe no more.
That's maybe why we found them, because the first 5 were easy to find.
Yeah, I guess so.
And then
the sixth one.
And then it's hard to check the bigger ones.
Right, they get large really fast, so it's hard to check.
Exactly.
Hard to check them after a while. There are some shortcuts. I'll put some notes in the further reading notes that I put up on Friday. I'll put some kind of tricks that people have used for checking whether these numbers are prime or not. Yeah, Rowan says law of small numbers, which I'm going to try and make real. Let's go. So that means the prime number theorem tells you how many primes there are, and it's kind of a really nice result. This is not the hand wavy part. This is the hand wavy part. So the probability alarm bells that a number is prime is kind of roughly 1 in log n. If you pick a random number of size about n, then, well, the number of primes is about n over log n. If you use that as a kind of density of prime numbers, then, okay, 1 in log n of those primes, 1 in log n of those numbers is prime. Really good question in chat. How do we know that it's n over log n? Proof not included in this live stream. It's a really good fact. Really strongly recommend university maths, partly for the reason that you get to learn the prime number theorem and why it's true. I'm not even going to give you a hint, I'm sorry. I'm just going to point at it and say, isn't that great? It's surprisingly simple as a formula. Get to the limit, you round up or down. So good point. This is not a whole number, and it's not that precise anyway. So this is not accurate to the nearest number of primes. It's not going to correctly predict the exact number of primes below 1,000, but it is. If you draw a graph, then it is a good first approximation to the number of primes as n changes. It's a shame you can't actually use this to decide if something is prime or not.
No.
That would be good. If it was very accurate, then you would detect it. It would go up by 1, and you'd say, "Aha, there's a prime." But it is approximate. This is okay. An approximately.
And if I can make a general comment,
yeah,
you realize in maths it's easier to make these kind of asymptotic statements than to make very precise statements. So this gives you an asymptotic statement as n goes to infinity, as it gets very large, and it's very approximate. It doesn't give you any information about any one particular number, but it gives you an overall trend, and those statements are easier in general.
Yeah.
But still very hard. I still wouldn't class this as an easy proof.
No. Sometimes in maths it's easier to prove things are sort of true for sufficiently large numbers that I guess that's sort of what we're doing here if you count the 6th term in a sequence to be sufficiently large. But there's I feel really bad for writing approximately equal to. Behind that approximately equal to sign, there's a lot of mathematical rigour that I'm not writing on the board. And yes, the prime number theorem is strong enough to say not only are there infinitely many primes, but yeah, here's an estimate of how many. Importantly, this number gets really large as you make n large. I guess because n grows faster than log n, log n kind of flattens out. N keeps
a lot faster.
Yeah. It's weird actually, it says that if we got human-sized numbers like 1 million or something, quite a lot of numbers are prime. Like natural log of 1 million is pretty large, right? Sorry, pretty small.
Natural log. Yeah, it would have to be.
Yeah, let me just check. This is the estimate. Right, so
I would say it's probably like 7 or 8.
It's 14.
14, okay, that's
it's
a
14. So this means that if you go up to 1 million, then roughly speaking, 1 in every 14 numbers is prime. which
Oh,
is
I thought you said 1,000.
sorry,
like
oh, a million. That's actually a factor of two. If you go to a million, roughly one number in 14 is prime, which is surprisingly dense. It means that if you're looking for a prime that's got 7 digits, you can just choose your favourite 7-digit number, and then check the next 20 or so numbers, and you'll probably find a prime. You don't have to look very far. But someone in chat has pointed out that 1 over log n, this does go to 0 if you make n large enough. Quite slowly, but it does get to 0. The density of primes goes down.
Yeah. I mean, it's crazy also. This might be a sidetrack, but that we don't even know the answer to the twin prime conjecture.
Oh, yeah.
So there's probably loads of primes that are right next to each other. But people who don't know the twin prime conjecture, it's the conjecture that there are infinitely primes that differ by 2. For example, 3 and 5, 5 and 7, 11 and 13, 17 and 19.
39 and 41. But yes, and people don't know whether it's true for twin primes. But I think people do know, recent breakthrough, people do know if you replace differ by 2 by differ by some number. No,
it's a pretty big number. It's in the millions.
Right. Okay.
But there's work to reduce that number now.
I think they've got it down. I can't remember how far they've got it down. Someone with Google will let us know. The thing I said about looking at about 20 works when the numbers are about a million. Of course, twin prime conjecture wants us to find infinitely many examples, so we'll have to get larger than a million. If you're looking for primes out at 10 to the 9, like a billion, then you have to go a little bit further to find each one, like 21 numbers. If you're looking for primes out at a trillion, you might need to go about 30 to find the next one. Is it down to 246? That's pretty good. 246 is a lot bigger than 2, but a lot smaller than who knows. Sorry. And as a shout out in chat for Vicky Neal's book, Closing the Gap, which is a description of the book. I really like the way that during Vicky Neal's book about closing the gap, she keeps saying, this is awkward to talk about because at the time of writing, the following is true. It's possible that before I finish writing the book, says Vicky, they'll just prove it. They'll get it down to 2 and it'll be done. It'll be sort of be over. Anyway, thing I was doing with the probability stuff, which I think is not very convincing, is that if you're asking about a Fermat number, then this thing is something like this, 1 over 2 to the n times natural log of 2, and so the kind of expected number of primes, if, and it's a big if, but if, let's put Fermat prime, sorry, it's a big if, if the Fermat primes kind of are random from the point of view of the from the point of view of the prime number theory, and if they're all independent random things, I've got them very, very not random. If they're all
do they even have to be?
Oh, I guess not, because of linearity of expectation, right?
Linearity, yeah.
Yeah.
You just need to.
Yeah, no, good point. Okay, fine. One fewer stupid assumption.
Okay.
But still hanging on to the, if they're kind of random, they're not. Then there'd be something like this going on for the sum of a geometric series. And a geometric series converges. You learn about this in A level, that the sum of those 1 over 2 to the n terms converges to some finite number.
In fact, that sum is equal to 1.
And with a log t, it kind of depends where you start. I've been a little bit hazy about whether you start.
Oh, yeah.
Like,
well,
we know that we know that the first few, we've checked the first few, so maybe we're checking like after the first 5 or something. I'm not really sure if you want to check. Like, what's the odds for the remaining ones? I guess we want to go from.
Let's start with that.
5 upwards.
Yeah.
In which case, this is 2, 4, 8, 16, something like
2 to the 32 plus 1. Yeah, that's definitely not in the ones that we have.
Yeah, it's tiny. Somebody says quite a nice thing, which is if you label everyone on Earth with a number, if you count everyone on Earth, then roughly 1 in every 23 people gets a prime, which feels quite nice in a way. That's a good way of describing the prime number density.
Yeah.
Does this fall apart when you get to smaller integers? Yeah, this does not work. This does not work really at all for small numbers.
Yeah, that's the thing about asymptotics.
Yeah. So
The whole thing of
do you want to tear it apart? you're doing a default in partly probabilistic techniques.
You mean tearing apart your argument?
Yeah, I guess so. Do you
So the argument rests on the assumption that these primes are uniformly distributed. However, as you pointed out, they have a specific formula. So in probability, in a way, you sample randomly. But here we're not sampling randomly. The sampling is very kind of directed in a way because we know exactly what we're choosing. We're not choosing a random number because, first of all, we're not choosing any of the even numbers. Whereas if you were sampling randomly, you would sample an even number, which with, like, if it's a number bigger than 2 with probability 0, it's a prime. Yeah.
The prime number theorem is about all numbers and the density among all numbers, but obviously you could do a different prime number theorem that only referred to odd numbers, and then you could do a different prime number theorem that only looks at things that are odd and not a multiple of 3.
And then one that's not multiple of 5, and you could continue like that.
If you refine the prime number theorem like that too much, then your prime number theorem is extraordinarily complicated. It just basically says, oh, I don't know, work out if it's prime or not, and then count them.
Yeah, exactly.
The prime counting function is, I guess, a theoretical thing. Like the number of primes below n is well defined. Maybe I should be using that instead, but nobody knows that. The questions are easy, but the answers are hard or unknown. Good, okay. So that's Fermat primes. In the thumbnail, I put the rather cheeky continue this sequence.
Also,
because,
before we leave,
yeah, go.
the probability that a number n is prime, if n is deterministic, then the probability that it's a prime is either 0 or 1.
Yeah. I was worried we would go here, right? Like,
yeah. Because if n has a distribution, if it's random, then you can talk about the probability of being prime being something different.
It sounds dangerously close. I know you're not saying this, but I'll say the thing you're not saying in case someone at home is thinking it. It sounds dangerously close to, well, when you flip a coin, it's either heads or it's not. So the probability is either 1 or 0. Is it heads or not? But somehow it's more deterministic, right? That's the point you're making.
Yeah, that's exactly it.
Right, in a way that my coin flip is sort of not. Okay. I wanted to change to talk about a different sort of prime number. Does anyone in chat, before we move on from Fermat numbers, does anyone in chat want to ask anything else? We can have a go. Or have you got any ideas for other sorts of prime numbers before I show you a different sort from my plan? So my stupid twist was I was going to think about, and I was maybe going to do this as an ad break problem, or kind of a break in the middle. We're a little bit past half past, but if you want to break here, I promise to do only stupid things for the next minute. The thing I was going to look at was 2 to the 2n, 2 to the n minus 1, instead of add 1 to subtract 1. But then I realised that these are stupid. Maybe chat can point out why this is a stupid suggestion. What about Mersenne primes? Yeah, good request. Mersenne primes are cool. They're almost in the same. They're also of the form 2 to the something, but you subtract 1, I think. I'm kind of combining ideas, right? So Mersenne primes involve subtraction. Fermat numbers involve huge powers of 2. I can't combine these. A in chat wants to know if we can use modular arithmetic. Let me show you a modular arithmetic fact. So we learned about modular arithmetic last week. I'm going to give you a sense of what modular arithmetic can do. So this one, 17 ends in 7, 257 ends in 7, 65,537 ends in 7, and then all the rest end in 7.
That's an interesting fact.
It's all right, isn't it? It's all right.
Yeah.
I think you can
There's
prove it with
using the recurrence relation.
you could use the recurrence relation, right? So if it ends in 7, then when you subtract 1, you get a number that ends in 6. You square it and you get something that ends in 6, and then you add the 1 back on. You can also prove it with modular arithmetic ideas about this 2 to the 2 to the n object. And maybe more seriously, rather than just saying they all end in 7, you can do some tricks to talk about what the prime factors could be. There's this thing I want to put in the further reading, but when Euler factorised the next one up is huge, and it's a multiple of 641. That's its smallest prime factor. So the thing you imagine at first is Euler just sitting at home checking prime numbers until he gets to 641, but because of modular arithmetic stuff, Euler knows that he only has to check numbers of the form 64n plus 1, things that are 1 mod 64, 1 more than a multiple of 64. So actually he only had to check 10 things to potentially be factors of this huge number, the next one. And 641 works. So there's some modular arithmetic around the place for how you might try to factorise these things. Further reading gets posted to the Maths Club website. Link is on screen at the bottom left to our homepage, where you can also find 70 past episodes on a variety of other topics, and almost all of them, and some of them have further reading notes, which I usually write the following day. Why not the first two? Yeah, I know. It takes a while to get going, right? And then it gets stuck. I guess that's weird. First two don't end in 7. And why is that only true about last digits, not the last 2 digits? The last 2 digits I'll leave as a homework problem. What's going on there? I think it settles down. I'm not sure actually.
So for the last 2 digits, you'd have to like mod 100.
Yeah. So last digit is more 10. Last 2 digits more 100. Akil says in chat that my invention, James primes, terrible idea because 2 to the n is even. So this is the difference of 2 squares. I guess we should check small numbers, right? Because maybe I get lucky on this one, but I do not get lucky on this one. I get
That one's one.
Even that's not prime. Difference of 2 squares, this factorises like this.
The next one might be prime though.
Do you think?
Yeah.
You're giving me hope. I don't know about hope. Oh yeah, hang on. Yeah. Oh, you've given me good hope. Number 3.
We found the unique James prime.
The unique James prime. Oh, brilliant. I'm naming after myself. Wait, hang on. I just need to change. There we go. Cool, right. Copyright. Maybe all the digits settle down eventually. I love this. Chat is doing sensible, serious maths. I'm messing around with naming primes after myself. I want to tell you about a different sort of primes, which we didn't talk about before the live stream. So this is new for Leo, maybe. We talked about it a little bit. Okay. So there's a mathematician called Sophie Germain. She was working on Fermat's last theorem, which we mentioned quite a lot. It's the one about x to the n plus y to the n equals z to the n. And a Sophie Germain prime is something she was using to make progress with the proof of that theorem. A Sophie Germain prime P is a prime such that, come on pen, we can do it, such that 2p plus 1 is also prime. So my example is 11 is prime. 11 is a Sophie Germain prime because 23 is also prime. Okay. Yeah, good work. People are now analysing the last digits of James numbers, which are the composite numbers in the James sequence, which is good. Carry on, chat. Okay. Here's the fun thing. 23 is my next example because 47 is prime. And then the question, I guess, or a question, can you keep going? So these are used, I'd say, while chat thinking about this, these are used, so Sophie Germain made some progress with Fermat's last theorem with these. I've heard that they've got some application to cryptography, which I've tried. I really don't understand the application to cryptography, but people sometimes call 2p plus 1 a safe prime. The pairing is p is a Sophie Germain prime if 2p plus 1 is a prime, and if the large prime is, then you call the large prime a safe prime if, oh gosh, that prime minus 1 divided by 2 is a prime. They can kind of pair up. So you can kind of build this chain, right, where the safe, I think the safe word comes from cryptography or something, that maybe they're more resistant to some sort of crypto thing, I don't know. Yeah, so it literally stops right after this, right? No, but what if you start somewhere else?
But that's surprising in a way, just by the fact that if you know already that a number would have to be a safe prime, then you can just check a smaller number for primality, I guess.
Yeah, well, that's the definition, that if you want, if your question is like, is 47 a safe prime, then you check a smaller thing for primality. I guess that's cool. That you've already done the hard work of finding out whether 47 is prime or not. Now, look back in your sieve for prime numbers or whatever, and just check whether that one's prime as well. Yeah, okay. I guess that's nice. Yeah, so people in chat are factorizing 95.
Do you know how many Germain primes there are?
I haven't. I don't want to say. I don't want to say, because if there are finitely many, then the answer to this sort of question is no, definitely you can't keep going. If there are infinitely many and I can prove it, then maybe that's a clue. So I'm not going to say either way. Okay. I think it will be interpreted as information on my chains question. A nice innocent chains question, right? Let's put some more Sophie Germain primes on the board. Let's see if I can think of any more. 19, because 19 goes to 39. It's kind of 79.
Yeah, that's prime.
That's prime, right? Yeah, and then 100. 80, 160, 159? I've got no idea. Is that prime?
I'm pretty sure, yeah.
Yeah, it's like
if it had a prime factor, it would have a prime factor less than 13, right?
True. It's not a multiple of 11.
It's not a multiple of 11 or 7.
Oh, yeah, I forgot about that.
Oh, wait. It's a multiple of 3. Because if you add the digits, you get something.
It is a multiple of 3.
Because you can add the digits.
True. It's also a multiple of 53.
Yeah.
Oh yeah, hang on. Also 39.
Oh yeah.
Sorry, it's a bit of a running joke. That I believe 39 to be prime. It's a sort of blind spot that I have.
It kind of feels prime.
It feels a bit prime, right?
Yes.
It's between some primes, like 37 and 41. Oh yeah, I can't start at 19. Actually, these multiples of 3 are quite annoying. So maybe a clever thing to do would be to avoid multiples of 3. Now we're thinking with modular arithmetic. So modular arithmetic says something like p is either 0 mod 3. That's stupid. That would make it a multiple of
then
3.
It's not.
Yeah, well, let's check 3 quickly to see what happens. 7. I'm now doubting my ability to multiply. Yeah, 15 straight away. 15. Not interesting. Okay.
No.
Or p is 1 mod 3. Or p is 2 mod 3. So,
so for 1 mod 3 we had 19, which clearly didn't work.
Yeah. 2p plus 1 would be
That'd be
2
0.
plus 1. 2 plus 1 is 3. Welcome to the maths club. I guess I'm going to write 3 mod 3, which is the same thing as 0 mod 3. It's a multiple of 3.
Yeah. Which explains why 19 would have the chain that ends immediately, because it was 1 mod 3.
Right, good learning experience, and generalizes nicely. That if you take a number 1 more than a multiple of 3. For people who have just seen the mod notation for the first time, it's shorthand for more than a multiple of, which comes up quite a lot in maths, so it's got its nice thing here. Somebody's looked up the thing that I didn't want to say and put it in chat. Fair enough. Okay, real talk. It's unsolved whether or not there are infinitely many Sophie Germain primes, which, as a consequence, you can infer also means that if there's an infinite chain, you're not going to find it. Because if you find an infinitely long chain, then as a consequence, you would have found infinitely many Germain primes. Maybe that's possible. You'd find it and then solve an unsolved problem, but yeah, kind of. That's not quite rigorous, right? That's just. I'm trying to work out if I'm limiting the audience, right? When I say, oh, it's an unsolved problem, so we're not going to solve it. Right? Hey, maybe we solve an unsolved problem on stream. That'd be fun.
That would be ambitious.
Yeah, and then it'll be the same stream where I thought 39 was a prime number, so that'll be really good. When there are primes, there are unsolved problems. Yeah.
That's a good rule of thumb for primes.
Yeah. Okay. I'm trying to think, can we do a more interesting chain? Has anybody at home found a chain longer than 3 numbers, 11, 23, 47? I'm calling it a chain. I'm writing them like this to just use an arrow for like double it and add 1.
So if we did want a chain, it would have to start with 2 more than a multiple of 3, right?
And be prime. So I guess, should we try 17?
17 goes to 35 immediately.
I'm an idiot. Okay, should we try something else?
23 goes to 47.
23 seems nice.
Oh, yeah, but 11 goes to 23, so that would have to be a smaller chain.
Right, okay. Something else I've noticed is the last digit seems interesting to me. Because, well, I can see it's kind of like something ending in 1 always goes to something ending in 3, always goes to something ending in 7, always goes to something ending in 5, which makes me think that this is not going to get better than this, right? It's 95, which ends in 5 on this occasion. We already did 23, yes. Sorry about the chat lag. Leo has an advantage of being on a direct call that doesn't go via Slido and back out the other side. 2 more than a multiple of 3 does kind of work in a way. In that 2p plus 2 would be 4 plus 2 is... No, what am I doing?
Wait.
2p plus 1.
What?
Thank you.
Wait, so by looking at the last digit, can you prove that the chain would have maximal length 4? Could, because if it ends in 5, it would have to not be prime.
Yeah, I think you probably want last digit 9.
Oh, okay, yeah. Oh yeah, because 9 goes to 9, yeah, you're right.
9 is nice because you get back a number that ends in 9. It's the reason I wrote 19 on the board. Hey, people in chat have got several. Somebody has put 5, anonymous person has put 5 on the front of this chain, which is a great idea.
Yeah.
I'm going to put 2 on the front of this chain. We're joining in. Yeah, last digit 2 is pretty bad as well. And if your last digit is 2, then I'm suspicious about whether or not you are prime or not.
Yeah, I mean, there's only one with last digit 2. It's the one you already wrote on the board.
Yeah, do I mean a 1 here? People are correcting me in chat. I think I mean 2 or 3. Oh, well, never mind. People can fix it at home if they want to. Okay, so once you've had the idea about ending in 9 and being 2 more than a multiple of 3, actually it rules out quite a lot of starting points. We're looking for starting numbers that are prime, end in 9, and a 2 more than a multiple of 3. Like, gets rid of...
Yeah. And we've checked 19,
We've
and
checked
9
19.
isn't prime.
Uh,
And then that gives us 29
yeah.
and 59, but 29 goes to 59.
Yeah, so our only hope of finding a nice chain is to start something like this. And people have found longer chains. I'm pausing because I'm not certain this is going to be one, and because I don't know if 119 is prime or not. This is from the person who didn't know whether 39 was prime or not, so he's well outside his comfort zone now. It's me.
It's not divisible by 3
Good.
or 5
I think homework.
or 11.
So here's a claim. So you saw
I'm
in...
pretty sure 119 is prime.
Yeah, so I think this is going well so far. And then I've got to double it to get some enormous number. So
239.
yeah, well, I have no idea if that's prime or not. It's not a multiple of 3.
No idea.
And it's in 9.
Yeah.
Yeah, who can say that's not. Claim, you can't have an infinitely long sequence.
Oh.
Infinitely, that's terrible. I hate that. I regret writing that. Here's why. Oh, a cool in chat has gone 89, 179, 359, 719, 1439, 2879. I haven't checked if those are prime, but that would be a sequence with 6 things in it.
Okay.
Okay, here's my proof. So the sequence that we're generating goes like this.
Mm-hmm.
A tiny bit of trust me bro in here, but if I repeatedly double then add 1, then I get, so after doubling this I get 4p plus 2 plus another one 4p plus 3, and then I get 8p plus 7, 16p plus 15, and there's a pattern here. You get things like 2 to the power of n times your prime p plus, and then this extra bit
2
is
to the n minus 1.
Yeah, 2 to the n minus 1. It's like the previous number. Power of 2 and the previous number.
Yeah.
Now. Eventually, two to the n is 1 more than a multiple of p.
Ah.
Because people who were here last week, people who were here last week saw Fermat's little theorem,
It's 1 mod p.
which says that
Wow.
in particular if you do 2 to the power of p minus 1, well, you've been plunged into darkness, sorry Leo. 2 to the power of p minus 1, you get 1 more than a multiple of p. That's not quite the version of Fermat's little theorem that we did last week, but it's pretty close. So I'm going to state it, and maybe I'll link something in further reading to explain the small thing that's happened here.
Wait, is this not Fermat's little theorem?
This is. We did the version. The version we had last week was 2 to the p equals 2 mod p, and there's just one line of argument that I'm skipping for why you can divide both sides by 2. And we had the way we wrote it was a to the p minus a is a multiple of p, and I just want to divide that by a, which is sneaky, but I am allowed to do that, I think. So this says that after a while, this 2 to the n term here will be 1 more than a multiple of p, which means that 2 to the n times p plus 2 to the n minus 1 is a massive multiple of p.
Yeah.
My starting prime. So if you start with 29, this says that after, oh my goodness, about 29 steps, you'll get a multiple of 29. And maybe it'll go wrong before then, but eventually I can prove that it goes wrong using Fermat's little theorem. Links. All about those connections between things. I'm going to give myself a little square as well on that. Okay. It's kind of cute, isn't it? This is that no matter where you start, this will eventually wrap around to being a multiple again of the same thing you started with. Cool. I just thought this was a neat way to link sequences of prime numbers back to what we were doing last week. Someone in chat's made me laugh by saying, what if your prime is infinitely large? Then we've got more problems. But prime number theorem says the probability of an infinitely large number. No, not really. Sorry.
Zero.
Yeah. Logging goes to zero, right? The probability that infinity is prime. No, none of this is good. Okay, cool. I think with the last minute addition of Leo's cool proof that you can only find Fermat numbers have to look like this. There's a reason that it's 2 to the 2 to the n. With the addition of your proof, I think we've managed to fit in a couple of nice bits of maths into a Maths Club episode. Follow up. We're not going to prove that there are infinitely many germane primes by cleverly making a chain of all of them, but there still could be infinitely many germane primes just out there in little bits and pieces. Some people are searching for longer chains. We don't know if there are arbitrarily long chains. Let's stop listing things that we don't know and call it a day at the end of the episode, I think.
What's interesting is that there's more things we don't know than there are things that we do know.
Say it again, sorry?
There's more things we don't know than there are things that we do know.
Oh yeah, classic. Yeah. More things we don't know. Yeah. Huh. Are there infinitely many? Yeah. There's only finitely many things we know. No, never mind. Let's not. I was going to maybe say there are about, on the grand scheme of things, maybe about 5 things that we know, and infinitely many things we don't know. Goodness me. Right, okay. At the end of the episode, we say thank you to our supporters. We're supported by the Mathematical Institute at the University of Oxford, and also by Jane Street. You can find out more about Jane Street on the Maths Club website, which is also where we post further reading notes. The day after the live stream, I sit down and try and find citations for anything random I said during the live stream, and try and find extra things that you might be interested in if you like the maths that we had during here. Also say thank you to Leo. Thanks, Leo, for coming on stream.
Thanks for inviting me.
Thank you to people in chat and you watching at home. We'll see you next week for another episode of the Oxford Online Maths Club. If you want to see more Oxford stuff, there's more stuff on this channel. If you want to see more of me, I'm streaming on Twitch as well under my own name. So you can find us in various places doing various things. But we'll see you in 167 We'll see you in 167 hours from another episode of the Oxford Online Maths Club. Take care. Bye.
Thanks, Julian.